Hi everybody, we're going to summarize the key points from the quote-unquote quiz that we took and we discussed a little bit in class. I will try to show you some videos to highlight some of the concepts here, especially this idea of frame of reference, because it's pretty cool and it's not something you normally think about. So let's just start with the definition. To move is to change your position, all right? So by definition, it's a change in position. So you can go from point A to point B, right? That's called translational motion. That's what we're going to study most about. A car moving down the road or you running along a track, you end up someplace else. So you got a different position. You did that through time, and we can start looking at things. We will eventually study rotational, where you go round and round. Think of something spinning around like a merry-go-round or a top. That's a little bit more complicated, but we'll do that at the end of the unit. And then there's even vibrational, which is the most complicated mathematically. And we'll study that at the very, very end of the unit. Now, this is the part I really want to focus on, okay? How do you determine if something is moving or not? You do that by not looking directly at the object itself. If you could only see the object and nothing else, you have no idea if it's moving or not. You have to look at the object relative to its background. Okay? So you're looking at what's underneath, behind, above the object that your eye and brain are coordinating to say, okay, the background doesn't seem to be moving because it's a wall or it's the ground, something else, and therefore this thing is changing position relative to that, so we can say something is moving. So implied in every statement of something moving or not is a frame of reference. And that's our fancy term. Okay? When I ask you, is this car moving or not, you're going to say yes or no because you're looking at the background of the earth. Your frame of reference is the ground. So that's the most common one. So I'm going to put ground / earth, right? Because if you look at the ground, it doesn't look like it's moving unless you're on an escalator or in a river or, in a supermarket, the little conveyor belt. Okay? Because the ground always appears to be not moving. Yet we have a contradiction there because you know the earth is spinning and it's going around the sun. And so if you are off the earth, let's say on the moon, and you could zoom in on the earth, you would see someone sitting still in a classroom as moving because they're going around you. They are spinning. So in a frame of reference of the moon, you do appear moving. On a frame of reference on the earth, someone sitting in a classroom would not appear to be moving. So it's really, really important to understand, and I really don't have a statement for this, but I guess I should, is that all motion that's implicit in this statement here is relative. It depends on what frame of reference you're in. And I'll elaborate more examples later, but probably the most interesting one is when you're in a car going down the road. Okay? If someone is standing on the side of the road and you're using the ground as their frame of reference, they'll say you're going right by at 20, 30, 40 miles per hour. But if you're in the car and you look at yourself, you're just sitting there. You are not moving relative to the car. You look out the window, you don't see yourself moving. You see the background moving. Everything is going backwards. The trees, the buildings, people standing there. And if you said, no, I'm sitting still, it's the ground that's moving, you're perfectly valid in saying that. Just as someone who's standing on the ground is perfectly valid in saying you're moving forward. So depending on your frame of reference, you can disagree on whether something is moving or not, and both of you can still be right, or at least not wrong. So it's a very interesting thing. We never really think about it because for almost all circumstances, the earth, the floor, is our frame of reference, and that's common to most anybody, so they'll agree whether something is moving or not. And piggybacking on that idea, in your own frame of reference, I don't care where you are or what you're doing, you will always see yourself as not moving. So I use the car example. You might say, no, I'm in a car and I'm moving. But, well, okay, let's stop and think about that. Let's put you back on the earth. on a stationary ground. You say, well, I'm not moving. True, relative to the ground, but relative to the moon or the sun or outer space, you are moving. So which is it? Are you not moving or you are moving? The answer is, well, both. I'm moving relative to the outer space. I'm not moving relative to the ground. I'm not moving relative to somebody standing next to me. So it's a really interesting phenomenon. It can sometimes trick you, so I'll try to show you some videos to show you this. All right, moving on. Measures of motion. This is really where we're going to spend most of our time. How do you measure? What do you measure about motion? And there are three fundamental measures, and then there's actually three derived ones. Derived means they come from the fundamental. So the fundamental measure of motion is first position, right? If motion is defined as a change in position, then it would make sense where you are. Now, position can be measured as a distance, and as we'll eventually learn, or a displacement. They're very similar, but they're not quite the same thing. Okay? Now, usually what we use as a variable for position is an x or a y. Okay, x usually means horizontal, y means vertical. Sometimes use d, but not often. The other one, next one, is when you change position, it takes time to do that. So a fundamental measure of motion is how much time did it take, and that's given a t. And the last one is probably the one you didn't come up with, and that is direction. Okay, it is very important to establish what direction you're doing. And if we get formal with direction, normally you can say north, south, east, west, left, right, up, down. But if you want to actually quantify direction, you usually go with an angle theta. So I'm going to guess some of you didn't say this, you didn't say all three of these. You came up with other things. You probably came up with derived measurements. So one is speed. Okay, and we'll eventually define it, and speed is usually designated with a v. Okay, the other one is acceleration, and that's designated A. You've all heard about accelerating before. That's the most complex of the ones we're going to study, so that'll come last in our development of sound, or excuse me, of motion. And the third one is really related to speed. I probably should have put a second. It's not like there's an order. There's velocity, and that's also given the designation V. In fact, speed I'd put absolute value signs around it, whereas velocity I would just put the V there. Okay, so these three right here derive from these three there, and we will learn how they develop in further discussions, labs, etc. Okay, so I'd like you to try the following example, see if this frame of reference concept is making any sense. I'll do the first one for you. So we have a situation. We are on a very fast moving train, okay, and this is relative to the ground, and it's moving westward. On the train is a passenger. Passenger's name is Biff, and Biff is walking toward the back to the dining car. So we're going to ask questions about how we see Biff moving from different frames. So I'm asking in each of these four, a sitting passenger sees Biff moving ... I want you to answer either east, the direction, west, or none, not at all. I'll just put none. Okay? So you should be able to determine that based on the information given if you read it carefully. So like I said, I'll do the first one. So let's say there's a passenger sitting on that train. Okay? They look at Biff. What direction would they see Biff moving? Well, if I look at the information, the train itself is moving westward. Well, I'm not outside the train, so I really don't see the train moving. I just see Biff. So what do I see Biff doing? He's walking towards the back. And back is opposite of east or west, so he would be moving eastward. So try the following three. How would Biff see himself? How would he see the train moving? And then how would a person standing on the ground seeing Biff move? Pause this, answer these, and then I will give the answers. Okay, so I'm going to go Biff sees himself. So if you go back to the notes, I said you always see yourself doing what? You should have had not moving. Or none, I guess. Okay? So if Biff looks around him, he sees the sitting passengers moving by him. He sees the floor moving. He sees the walls of the train moving, but he does not see himself moving. He's just standing there. Yeah, his arms and legs might be moving relative to him, but his whole body does not seem to be going anywhere. What does he see of the train? This is the one that gives students the most trouble. Okay, he's in the train. He can still see the train, just from the inside, not the outside. So if he's looking around at the train, especially at the walls or the seats that are attached to the train, they seem to be going in the opposite direction of him. Okay, so if he's facing west, even though he doesn't seem to be moving west, he'll say everything's moving in the opposite direction. So he will say that he's facing east. He'll say the train is moving westward. Okay, so if you don't buy that, pretend the train is the earth and you're on the earth. When you start walking, you don't see yourself moving. If you look at the ground, you see it slipping underneath you in the opposite direction. This is the exact same thing. All right, a person standing on the ground sees Biff moving. Moving wow. All right, and this is where a diagram might be helpful. So this represents, I know this is awful, the train moving this way. We'll call that west. Biff is facing this way, moving east. So I'm standing on the ground outside it. What do I see happening? Well, you could argue east, west, or not at all. And so if you're thinking that, you might be thinking, well, it depends on how fast the train is moving and Biff is. And you'd be absolutely right. And so we're anticipating where we're going to go next. But we do have an important clue to tell us which of the possibilities are occurring. And that's the fact we have a really fast train. So we have a fast train and Biff is walking. We can be pretty safe in assuming the train is moving faster than Biff. So even though Biff, relative to the train, is moving this way, relative to us, he's going to be moving that way. He's going to be going forward with the train, just not as fast as the other passengers. So if I have passengers here and here who are sitting there, these people are going to advance relative to me more than Biff is, because Biff is going to not advance as fast, which would be consistent with the people in the train seeing Biff move towards the back while they're not moving at all. So it all hangs together in an odd way. So what we want to do next is introduce, what if you have something like this, and I were to tell you this is moving 50 units to the right, and Biff was moving 5 units to the left, how fast would we see him moving? And this is going to introduce an important concept that comes with every measurement. That's called vectors or scalars. So that's going to be another tutorial that's going to help us eventually answer the problem on the very back of this sheet. But you don't have to do this sheet right now. Just for right now, make sure we understand this idea of frames of reference.